Hi there. So I'm going to walk through how to find the distance between two complex numbers on the complex plane. And I'm also going to look into how to simplify a radical because you're going to come up with radical expressions when you do that. And simplifying radicals can sometimes be frustrating. So let's go. So what I have on my screen is the complex number plane. You have the imaginary plane, sorry, the imaginary axis, which is the vertical axis, and you have the real axis, which is our horizontal axis. And I have two numbers here. I have z, which is 1 plus 2i, and w, which is 3 plus 5i. And those might have come from solving a quadratic formula or something like that that had within it the square root of -1. So we can look at how we plotted these briefly. So 1 is our real component for z, and 2 is our imaginary component for z. So we would go over 1 and up 2, over 1 and up 2, and there's z. Let's look at w the other way. So w is over here. It is over 1, 2, 3, and it is up 1, 2, 3, 4, 5. So we should find 3 plus 5i. So we have 3 plus 5i, 3 being the real and 5 being the imaginary component. And we're going to look at the distance between the two. Just like in Khan Academy, where Sal says it's the Pythagorean theorem, we are going to be using the Pythagorean theorem, which to find this length between the two. Let's see if we can draw that length between the two. So here we go. All right, there's my stylus. Sorry about that. So we're going to go from here up to here. And we're looking for that length, which is the hypotenuse of a right triangle that has a horizontal side along here and a vertical side along here, and forms a right angle between the two. And we remember that every right triangle obeys this relationship between its sides, where a squared plus b squared, which would be this length plus this length, in either order because it's addition, is always going to be equal to the hypotenuse squared. So what we're looking for is this length over here. And so we can find a and b. So we'll make some parentheses here for what's going to be a and what's going to be b by subtraction. And this is the part that I think Sal went over too quickly. So this length right here we'll use for our horizontal will be the real component of w minus the real component of z. So the real component of w was 3, and the real component of z was 1. And you see that we're over here at 3 and down to 1. So we'll have 3 minus 1 for that part, for a. And then for b, we have the imaginary component of w minus the imaginary component of z will give us this length here, which would be 5 minus 2. And let's write those in. So we end up with 2 along here when we do that subtraction, and we end up with 3 along here when we do this subtraction. Now, if we had had a negative number here, like if instead of plus 5i, w had been 3 minus 5i, 1, 2, 3, 4, which would be all the way down here, then this process would still be the same, and we would just have a negative sign right here as we put it in. Similarly, if we were subtracting 2i for the z, then we would have minus -2. Just keep the negative with the number that's going in. So when we do this, we would have 2. All right, not writing. Not sure why. There we go. 2 squared plus 3 squared is going to give us our c squared that we're looking for. So that's 4 plus 9, that's 13. So 13 is equal to c squared. That's squared. So that's not what c is. That's what c is when it's squared. So to find out what c itself is, we take the square root of both sides, the square root of 13 on that side, and the square root of c squared is c. So that side's done. So we end up with c is equal to the square root of 13. This is a real number. So the distance between 2 points in the in the complex plane is a real answer. It doesn't have any I or imaginary component to it. Now, what happens if instead of getting the square root of 13, we had ended up with something like the square root of 50? as C, or the square root of 48. That, if you try to put that into Khan Academy, is marked as either not yet, keep working, or that's incorrect, you need to simplify your answer, because this is not in its simplified form for a radical. So we want to take out all the things that are perfect squares that are in the radical. And I'll show you how to do that on the next panel. I'm going to use this 48, and then we'll come back and see what we would get for 50. So let's go to the next panel, next frame. Here we go. So this is the relationship that we'll be using, that if you have a square root of two things that are multiplied, they have to be multiplied, or division would do the same thing, but addition and subtraction do not. So the square root of the product of two numbers can be expressed as the square root of the first number times the square root of the second number. For example, if I had the square root of 48, I happen to know that 48 is 16 times 3. And I'm choosing 16 as something to change it into because of what happens 2 steps down the road. I did not want to draw that. So if I had the square root of 16 times 3, that's the same as the square root of 48. I can rewrite that using this property as the square root of 16 times the square root of 3. Now I can evaluate the square root of 16 because it is now an entire piece all of its own, and I know that the square root of 16 equals 4, because 4 times 4 is 16. So this piece gets replaced with just the number 4, no square root around it anymore, times 3. Because this one does not simplify, I leave it as it is. Then I write it again without the multiplication between, because it means the same thing when it's just pushed right up against it. So 4 root 3, which is different than the notation that would indicate the fourth root of 3, which is when you put that 4 up here on a little platform as part of the square root symbol. That is different, so that is not what we're doing. So this is 4 times the square root of 3, which is the same as the square root of 48. And this is called simplifying a radical. And if you need to watch some videos on simplifying a radical, the Khan Academy ones are great, but you might not have known that's what it's called, or that that's what was going on. So let's go back to the last one and see. So now we're looking at square root of 50 is something that's also not simplified. Let's think about what we could do with that one. So I'm going to come over here. I've got the square root of 50 as my distance. And I could write that as, well, let's see, what is 50? 50 is 5 times 10. Neither 5 nor 10 is a perfect square. So that's not very helpful. But it is, I could take the 5 times 10 and write it as 5 times 5 times 2, because 10 is 5 times 2. And let's extend that one. So now I've got the square root of 50 is the same as the square root of 5 times 5 times 2. Because 5 times 5 times 2 equals 50, I can replace 50 with what it's equal to. And right here, I've got a number times itself. So that means that that's a perfect square in here. That was 25. So I could have this equal to the square root of, well, we could put it back into 25, because maybe we're more used to thinking of the square root of 25 as being 5 than the square root of 5 times 5 being 5. They are the same thing, so we could have gone either path. And here's times square root of 2, because of that property that we used on the other page. So I've got the square root of 50 is equal to the square root of 25 times the square root of 2. And then I can evaluate this first one without that evaluation changing anything in the second one. So I would have 5 times the square root of 2. And I should probably rewrite it just by pushing them up against each other. So 5 square root of 2 is the same as the square root of 50. So hopefully that's going to reduce some of the frustration that you might have felt about expressing the answer and being told that it was wrong when all the steps you did were right. And hopefully this also helped in going over the distance between 2 points on the complex plane as a way of using something called either the distance formula or an application of Pythagorean theorem. They're the same thing. And I'm hoping to post a few more of these about other topics as we go. Hope this helped. And now you have to bear with me while I move over and stop the recording. Take care.